Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to take a look at doing integration by trigonometric substitution. We've taken a number of patterns of integration, but there are certain integrals that you may encounter that can't be done by any of those patterns and can't be done by integration by parts. We're going to take a look at integrals that involve a certain form that we can use trigonometric substitution to integrate. The forms are square root of a squared minus u squared, where a is a constant, u is a function. So an example of this form would be this integral, where we have an x squared as well as square root of 4 minus 9x squared in the denominator. We don't have a pattern that will allow us to integrate this function. Another form that we can do by trig substitution is one involving the square root of a squared plus u squared. So this would be an example of that. Remember, when you've got a function to the power of 3/2, that denominator 2 means a square root. So this cannot be integrated with our general power or any other form. So we're going to use trig substitution on this one. By the way, when you have a squared plus u squared, it could be written as u squared plus a squared. It's the same. So here I have u squared plus a squared. It's the same as a squared plus u squared because it's addition. The third form is if you have the square root of u squared minus a squared. So your function squared minus your constant squared. An example of that would be this one, where you have u squared minus a squared in the denominator with the square root. We can't use our general power, we can't use our inverse trig, so we need another method. So I'm going to introduce you to a method called trigonometric substitution, which seems very lengthy, but it's very powerful in that it will allow us to find each of these three integrals. So let's take a look first at doing an integral of this form, and we'll do this example. So whenever you have an integral of that form or containing that in it, the trig substitution that you're going to do is you're going to let u equal a times sine of theta. Just trust me with this, just follow along. You'll see that we'll eventually end up with a function that we can integrate. So before I do that substitution, let's define a. Well, we know that a squared is equal to 4. Therefore, a is equal to 2. U squared is 9x squared. Therefore, u is 3x. So the substitution we're going to use is we're going to let u, which is 3x, equal a, which is 2 sine theta. And I'm going to isolate x. So x will equal 2/3 sine theta. So I'm going to replace any x's in my integral with 2/3 sine theta. So I'm changing to another variable. I cannot use dx if I'm changing to a variable theta, so we have to express d theta. So we differentiate this. We take the differential of x. It will be 2/3 times the derivative of sine of theta will be cos of theta, d theta. So replace my x's with this and dx with this. It's going to look a lot uglier before it looks better, so just stick with me. So my integral will be dx, which is 2/3 cos theta d theta, divided by x squared. X is 2/3 sine theta. And then I'll have 4 minus 9 times 2/3 sine theta squared. Let's do a little bit of simplifying. So I've got 2/3 cos theta d theta. When I square this, I'm going to get 4/9 sine squared theta. I'm also going to get 4/9 sine squared theta here. So let's multiply that by 9 and it will be 4 sine squared theta. When I square this, it becomes 4/9. When I square this, So 9 times 4/9 will just be 4. The 9s will cancel. Now I'm going to pull out these coefficients. So I'll have 2/3 divided by 4/9. And I'm going to factor out a 4. Two-thirds divided by 4/9 will be 2/3 times 9/4. So that reduces to 3/2. And then I'll have cos theta d theta over sine squared theta. And then I'm going to break that square root of 4 up. Square root of 4 is 2. I can pull that 2 out front here. It's in the denominator, just to clean it up a little bit. Now I can use one of my trigonometric identities, my Pythagorean identity, that says cos squared theta plus sine squared theta equals 1. Therefore, cos squared theta will equal 1 minus sine squared theta. So I'm going to replace this with cos squared theta. So I'll have square root of cos squared theta. Now, square root of cos squared theta can be written as cos theta. We can cancel a factor of cos theta out of the numerator and the denominator. And I can replace 1 over sine squared theta with cosecant squared theta, one of my basic trig identities. This is one of my basic trig patterns for integration. I can find the integral of cosecant squared theta d theta. It's simply negative cotangent theta. So this integral will be negative 3/4 cotangent theta, and I'm not going to worry about my constant yet because I'm not done. I have my integral in terms of theta, but I want my integral in terms of x. In order to do that, we need to express theta and x in terms of our right triangle. So in order to define the sides of my right triangle, if theta is this angle here, I need to go back to my substitution. I know that 3x is equal to 2 times the sine of theta. Therefore, the sine of theta will equal 3x divided by 2. We know that the sine function is the ratio of the opposite side to the hypotenuse. So in terms of our right triangle, the opposite side is this side, and that's 3x, over 2, which is the hypotenuse, which is here. We're missing this side, so in order to find that side, I'm just going to use my right triangle theorem. I'm just going to call that question mark. So in order to define that, I know that 3x squared plus that question mark squared will equal 2 squared. So 9x squared plus that question mark squared will equal 4. So that side will be square root of 4 minus 9x squared. Now that I have all 3 sides defined in that right triangle, I can go back to my answer. And how do I express cotangent theta in terms of x? Well, you have to understand what the cotangent ratio is. It's defined as the ratio of the adjacent side to the opposite side. So the adjacent side is square root of 4 minus 9x squared. The opposite side is 3x. I'm going to add my constant of integration now, and the 3 will cancel, so this can be simplified to be negative square root of 4 minus 9x squared over 4x plus a constant of integration. That would be the integral of this function. So it's a lot of manipulation, and it's easy to get lost, but when you have an integral of this form and you cannot integrate it by any of the previous patterns, then you can try this substitution. Find your x, find your dx, do all of the substitutions with those. See if you can integrate the function, your new function, with all those substitutions done, and then go back to the x. I think it's important that you practice some questions of this form before taking a look at the next video. In the next video, I'm going to do the other two forms, but I want you to get a good grasp of using this because the other ones use different substitutions. So when you're ready, I'll see you on the next video.